All right, this is exponential functions, part 3. So now we're going to look at modeling real-life scenarios. All right, so the graph represents a bacterial population Y after X days. Find the population after 5 days. All right, so if we look at the graph, we have 0, 3, 112, 248, 3, 192, and 4, 768. All right, so with that, we know that we can create our table of values. So we have 0, 3, we have 112, 248, 3, 192, and 4 and 768. All right, so why am I putting that into a table? I'm putting that into a table so that we can look to see what the change is. So we go from 0 to 1. As our x is increased by 1, what happens to our y values? So to get from 3 to 12, we are multiplying by 4. 4 times 12 is also 48. 48 times 4 is 192. And 192 times 4 is 768. All right, so by looking at that, we can see that as x increases by 1, we have to multiply by 4 to get to the next y value. We also can see what our y-intercept is. So 0, 3 is given, okay? So we can see that our y-intercept is right here, 0, 3. It looks like it's on 0, 0, but that's because this is going by hundreds here. The population's in hundreds. So that's at 0, 3. So what we can do is say y equals, we know that our exponential equation is y equals ab to the x. And we have a is 3. That's our y-intercept. And we know b is 4. So we can just substitute y equals 3 times 4 to the x power. So first thing we have to do is write the equation. And then once we have an equation, we can find the population for any number of days. But this says find the population after 5 days. All right, so if we want to know after 5 days, that means let x equal 5. So y equals 3 times 4 to the 5th power, and we can see what that is. Let's see. All right, so we got 3 times 4. We're going to raise that to the 5th power. That's probably going to be a pretty big number. It is. So y equals, what was that, 30, 45, 30, 72. 3072. So we can say, it says the graph represents bacterial population. So we can conclude that there are 3,072 bacteria after 5 days because we substituted 5 in for the number of days. All right, so I typed that answer here so you can read it a little bit better. So there are 3,072 bacteria after 5 days. So when x is 5, the y value is 3,072. All right, make sure we answered all the questions. The graph represents bacterial population y after x days. Find the population after 5 days. So that was the only question. So we can conclude that we are done. Example 6. So it says the table shows the temperatures y in degrees Fahrenheit of coffee x minutes after pouring a cup. Use technology to find a function that fits the data. Predict the temperature of the coffee 10 minutes after it is poured. All right, so when they give us a table of values, if you remember, we did this with linear equations. So now we're going to do it with exponential equations. It says use technology. So we're going to use our calculator to find a function that fits the data. All right, so let's go to our calculator. And if you remember, if you go to Stat, And number 1 is edit. So stat number 1, this will allow you to enter numbers in your calculator. So if you hit enter, okay, you can pause the video and enter these in so you can follow along with me. To save time, I went ahead and entered the table in. So just enter these one at a time. Put X in L1, Y in L2, and then unpause the video when you're ready to continue. All right, so use technology to find an equation. So we're going to go back to stat, and we're going to go to calculate. So remember before we did linear regression, that's when it was a line. So now we know that it's not linear regression, that this is exponential regression. Actually, it doesn't say exponential regression. I'm assuming it will be, since that's what unit we're in. But let's look at the scatter plot first to see what kind of equation we're looking at. So if I go to second y and I turn on my stat plot, what it's going to do is it's going to graph these as just dots on a graph. So we want dots, L1 and L2. All right, so I'm going to enter through all of this. And then let's hit graph. Now remember, this is a 10 by 10 graph. Look at these numbers, 175 to 75. So my x's are between 1 and 10, but my y values need to be changed. See, if I only have y's up to 10, that's why no dots are showing up. So I'm going to go to window, and I'm going to go to y maximum. All right, my y maximum needs to be bigger than this largest y. So instead of 175, let's put like 180. All right, it's using a scale of 1. Let's maybe use a scale of 5. And then hit graph. And that's going to show you those points. So it does look like a curve. It looks like exponential decay to me. All right, and we're talking about temperature in degrees Fahrenheit of coffee. So the temperature would be going down after so many minutes. So it would represent exponential decay. All right, so let's go back to stat now that we've looked at the scatter plot. And let's do calculate, and let's see what happens. So let's calculate. Scroll down till you find exponential regression. There it is, EXP-REG, so hit enter. And we're going to pull from L1, L2, and yes, we want to calculate. So this is going to be our exponential equation. So you can see that it gives us an A of 173.95. We could round that up to 174. And our B is 0.9, so it's decay, it's going down. And then that would be raised to the x power. Now, R, if you remember, R tells you how strong a correlation it is. So R is negative 0.999, which means that's a very strong negative correlation. So let's write down our equation. So we're going to have y equals 174 times 0.9 raised to the x power. Now, if you want to check this and see what it looks like based on the points, because this shows that it's a very strong correlation, which means this equation that we wrote based on these points that we put in the table should be a very good indication. So let's go to y equals, and then I'm going to do vars stat number 5 equation, and it's going to copy that equation over in my y equals, and then hopefully it will graph that, and we can see if that line looks like the scatter plot we drawed. And you can see now that it's graphing that equation, it's going through every single point on there. So that's why it's a very strong negative correlation. So we can conclude that this is a really good equation, exponential equation, based on this data. And so we use technology to find a function. Now we need to predict the temperature of the coffee 10 minutes after it is poured. So time is your x value. So we want to know what this is raised to the 10th power. So y equals 174 times 0.9 to the 10th power. So again, we can use technology. We can just type this in, 174 times 0.9 raised to the 10th power. And this says that the temperature is going to be about 60.7. All right, so we can predict that after 10 minutes, the temperature of coffee will be about 60.7 degrees Fahrenheit. We know this because we used Fahrenheit up here, and X is the number of minutes. So this is just an estimate, but using this model, this exponential model that works very well, then we can conclude that. All right, in example 6, that's this example here. Identify and interpret the correlation coefficient and the y-intercept. All right, so the correlation coefficient, that was the R value that we looked at when we had our equation up here. Let's see if we can find it again. All right, so the correlation coefficient R equals negative 0.999. So R equals negative 0.999. Interpret what that means. That means this is a strong negative correlation, so the equation is a good fit. All right, it also says tell what the y-intercept is. The y-intercept is 174. A is your y-intercept here, and that's the temperature of the coffee when it was made, like original time 0. So when the coffee was made, that's when the temperature will be the hottest, and it was 175 degrees at that time. So your y-intercept is 175. All right, that's all for example 6, and that's all for exponential functions today.